So we're reviewing about spectroscopy, about the nature of spectroscopy and what it involves, and we're starting to consider IR spectroscopy, where we're looking at transitions at the level of bonds bending and stretching. Now, in the old days, by old days I mean even before my time, when you looked at an IR spectrum, the horizontal axis was registered in micrometers. So you were looking at wavelength absorbed, and when you looked at where a peak was, you would say this peak is at 3.5 micrometers or 1.8 micrometers, whatever it would happen to be. But going back at least as far as when I was in college, which was the late 1980s, by then they'd already completely made the switch to wave numbers. And those are funny looking. That's the way we write wave numbers. You can pronounce that as per centimeter or inverse centimeters or something like that. And it's another kind of frequency. Normally we're used to frequency being in hertz, which is per second. In other words, how many waves pass by a fixed point per second. In this case, this type of frequency is per centimeter. So in that case, you can think of this as meaning how many of the waves, how many of the little suckers can we cram into a centimeter? And so there's this many waves per centimeter. You can think of it that way. And so being a kind of frequency, this kind of frequency is proportional to energy. And in general, the higher the energy of absorption, the stiffer the spring, if we think of bonds as being like springs, which has its limitations, but doesn't do too badly. You could do worse. And the lower the energy of absorption, the looser the spring. And so you'll see. So as you may recall, you saw higher energy transitions at the left of the spectrum and lower energy transitions at the right of the spectrum. So there is a correlation table on page 373. What I would normally say, normally when exams were not open book, what I would normally say still, and I think it still applies, even though you can look at your book, I do not recommend memorizing that table. I don't think that's the way to go about learning what you need to know about IR spectroscopy. And we'll get to what I think is a good way to go about that. But especially, please be aware, all of those figures on page 373, they're only guidelines. They just tell you where peaks of a certain type usually show up. And I'm going to try to convince you that really there's only about 2 numbers that you need to memorize. I think 2 numbers is not too bad. And those 2 numbers, for my money, are 3,000 and 1,700. So those I really think are the only 2 that you need to memorize, if even that. But if you did have to memorize numbers, those would be the 2 I would recommend. And what I'm basically going to go through with you are just some examples of typical compounds to help you see where different functional groups usually show up. I'm just going to use them sort of as archetypes or examples. Just so I don't keep you in suspense, the best way to learn about spectroscopy, I think, is to look at a bunch of spectra and look at spectra of different functional groups. See if you can find the different characteristic peaks. And I have a website that I'm going to hook you guys up with at the end. I'm nearly positive it's that the URL is in my class notes. Let me also say, just to get you on the right track, I don't consider it possible to look at an IR spectrum and go, this is such and such a compound. I don't think it's specific enough to do that. You certainly couldn't do that with ultraviolet visible spectroscopy. Still, I don't think you can do that with IR spectroscopy. So where are we going with this? Well, can you look at a proton NMR or a carbon NMR spectrum and know what the compound is? Maybe not quite, but getting close. Now, if you're given a proton NMR spectrum, a carbon NMR spectrum, and an IR spectrum, and a mass spectrum, now can you tell what the compound is? Yeah, you probably can. So that's way at the end of the term. We'll get to those combination spectroscopy type problems. But in any case, as for looking at an IR spectrum and go, ah, that's acetophenone, you can put that worry right out of your heads. It's not possible. What you certainly can do, and again, I have an old exam posted. You can also get an idea of possible question formats from OWL. But I think what you'll see a lot of is matching. That kind of, I don't say that's the only type of problem you can ask with IR, nor am I promising any particular question format in your exam. But it does lend it to, the topic does lend itself well to matching, because what we get out of IR spectra is largely functional groups. What types of bonds, therefore, what functional groups are present, and equally important, which are not present, because we don't see them in the spectrum. Now, if you sent the info about OWL setup, I have links in the syllabus, so you can get that on Howdy or on eCampus. I've also put the in case you're asked for a course key, which again, I don't quite understand this. Sometimes some students get asked for course keys and some do not. It might depend what kind of package they're buying. But yes, that tells you where to go, and there's also a video there. I even got sent some time ago an email saying that through, I think, most of next week, they're going to be having help sessions on signing up for Cengage products. I will tell you, of course, nothing is due tonight. The soonest anything's going to be due will be a week from today. And I'm planning on getting the first OWL assignments up and running sometime this weekend. I might even do it today. When I went through the link in this bill, it didn't do a course key. Interesting. Well, again, it might, that might be it. It might also have to do with whether which type of OWL package you're buying. So, but yeah, there should be a link in the syllabus. Where was I? Oh, so we're talking about what to get out of IR spectra. So to start with, let me also put another worry out of your mind. Don't think of this as having to identify every single bloody peak. It's not possible. The only time it's almost possible is when you have like an alkane, which we're going to get to next. But generally, that's not the point. Usually, I think you'll find anything below round and about 1500 or 1450 wave numbers. You probably learned in lab, that's called the fingerprint region. And that means two things. First of all, it means it's highly characteristic for each given compound. And the other thing is we're not even going to try to identify all those peaks. And we don't need to in order to derive information about the compound. Uh-oh, Bella's jumped up in my desk. Here we go. I hope the cats are not bothering you too much. I should mention the reason that I let them in, besides that a lot of people are delighted with cats, the main reason I let them into the room is because if I didn't, they would sit at the door screaming the entire time. So I figured this is the lesser of two evils. They don't usually bother anything. Barnaby is already completely dead to the world, lying on the bed, dead asleep. And Bella might join him, we'll see. Anyways, so over here, they want to learn OChem. Well, they already know it all, of course. Over here, I've just got for you the spectrum of hexane. And this is, by the way, I got this spectrum from the website that I'm going to be linking you guys to, that I gave you the URL in the class notes. What's a lie and who knows what? They just want to learn organic. Wait a minute. Lost control of chat. My cat is trying to kill us. He might succeed. Cats are, I could tell stories, but anyway, this is neither the time nor place for that. So this could be considered pretty much the presence of absence, if you will, when it comes to an IR spectrum. This is what you will get if there really are no functional groups to speak of. Here we have just a saturated hydrocarbon. And so the main thing that jumps out at me, and I hope will jump out at you with practice, is we see all of these pretty strong peaks below 3,000 wave numbers. And I don't know why the dividing point turns out to be pretty much exactly 3,000, but it does. And I've already written that down for you here, so you can get that in your class notes, not to mention that it's already in your class notes anyway. But if you see any peaks just below 3,000 wave numbers like this, those are CH stretches where the carbon is sp3 hybridized. And that's pretty much all we see. These peaks over here, they might be CH bending or carbon-carbon stretching frequencies, maybe. I don't think we even need those to identify what's going on here. But certainly when I look at this spectrum, I can tell there's no alcohol, no carbonyl group, no carboxylic acid, nothing of that sort, nothing except sp3 hybridized carbons and hydrogens. So this is about the most blank spectrum you'll ever see. And really this is what I'm gonna do for you guys today. I'm just gonna go through a bunch of examples of IR spectra. I can't show, there's no time to show you every single possible thing you might run into, but I think we can get through the main ones at least. So any questions? I think you know the structure of hexane. Any questions so far? Can you recognize this is some alkane, or would you know this is hexane? The first thing, I would know that this is some kind of saturated hydrocarbon, but as to whether it's hexane or cyclohexane or pentane or octane, I don't think, I wouldn't know. And I don't think it's really possible to know. But certainly, like I said, looking at this, the main information we get is what's not there. Like I said, there's no carbonyl, there's no alcohol, no carboxylic acid. I don't see an aromatic ring. I don't even see any carbon-carbon double bonds. There's pretty much nothing. There isn't a difference between the IR of hexane and cyclohexane. Well, they might be a little different, but I don't think you'd find significant differences. And you can find that out yourself. I would recommend you look them both up on the website that I'm going to give you the URL. But certainly looking at it and go, this compound is clearly toluene. I don't know of any way to do this. Now, if we looked at the spectrum of toluene, which we well might in just a moment, I don't remember which aromatic compound we did, I think we'll be able to tell that there's an aromatic ring. That's true. And I think we'll be able to tell that there's both sp2 and sp3 hybridized carbons. That's also true. But picking it out exactly, I don't think is possible. Good, so this is a pretty boring spectrum, but any other questions just on this one before we start actually adding functional groups? But again, this is not about memorizing particular spectra. You might be able to tell it is cyclohexane and cyclopentane. Yeah, and of course, cyclopentane is a teeny bit, just a teeny bit more strained than cyclohexane. It would be interesting to look those up. I wonder what cyclobutane and cyclopropane would be if this website has those spectra. I'll also just mention that it's usually this website from which I get the spectra that I put on exams. So they'll probably look something like this. Ring stretch. I don't know that there's ring strain. Oh, I see what you mean. Yes, and it would be interesting to see if you can detect that on the spectra. I don't know. I've never looked into it. It's an interesting question. So much for hexane. Let's up the ante just a little bit. This spectrum is of 1-hexene, and I think you know the structure of 1-hexene, but I'll put it up here just in case. Do it in just 2 mouse clicks. You're going to be so jealous of me. It's kind of like the sketcher that you have in OWL, only a little bit more powerful, but not really different in concept. So here's the spectrum of 1-hexene, and we can already see it's a little more complicated. We've got a few more peaks in the fingerprint region, but even without going there, I do see at least one fairly prominent peak just above 3,000 wave numbers. And that it really does, for some strange reason, some strange coincidence, that 3,000 wave numbers is exactly the cutoff, or as close to 3,000 as makes no odds. But that CH stretch that's just above 3,000, that refers to the CH stretches for these three CH bonds, the ones that are on the sp2 hybridized carbon. And so you can pretty much count on that. I mean, I don't find myself running into exceptions very often, if at all. It would be interesting to compare this to hexane and see which of these are different. Those would probably be associated with the double bond. I wouldn't be shocked if some of these around 1500 are the carbon-carbon double bond stretch. That might be. There might also be some CH bending that's down here. Like I said, I don't consider it important to identify every single peak, nor do I think it's generally necessary. But we can tell from this that we've got, maybe we wouldn't know it's one hexene, but looking at this, I would know that I've got an alkene for sure. It's not an aromatic compound, and we'll see why that is in just a moment, I think. I would again know there's no carbonyl, no alcohol, no carboxylic acid, nothing extremely obvious like that jumps out at us. So I would know, and I would expect you guys to know by looking at this, that we've got an alkene. There's at least one carbon-carbon double bond, but really not so much anything else. Make sense? And again, the best thing you can do for learning about any kind of spectroscopy is just look at spectrum after spectrum after spectrum after spectrum. Just the website I will give you allows you to enter formulas, to enter names. You can look up compounds either way, and they may not have every single compound you can think of, but they've got a lot of them. So, just so that I'm not leaving you in suspense, let me just double check that this is at the end of the class notes. There it is. So you've got the URL there. I use that webpage all the time, and I will probably get most, if not all, of your IR spectra from that very website. They'll look just like this, except of course I won't leave the name of the compound up there. That would not be fair. All right, so with that, let's move on to the last type of hydrocarbon that we run into at all frequently, which is aromatics. Toluene, as I think you're aware, is methylbenzene. So there's toluene. And the spectrum of toluene is going to be similar to that of our alkene, in that we'll see some CH stretches above 3,000 wave numbers and some below. And again, that's because we do have one sp3 hybridized carbon, but we also have all of these other 5 sp2 hybridized carbons that have CH bonds. So that's, if you sort of mentally draw a line up from 3,000 wave numbers, you'll see we have them on both sides. And that makes sense. That's consistent with the structure. Other than that, I don't see a carbonyl, I don't see an alcohol, I don't see a carboxylic acid. Nothing like that is jumping out at me. So what's the difference between aromatic and alkene IR spectra? Usually what I look for is these small kind of, rounded and kind of pretty and symmetrical looking peaks that are not too far below the baseline. Those represent overtones, actually. They're overtones of other peaks elsewhere in the spectrum, in the same sense that you can get overtones in sound. Those of you who play a brass instrument know very well about overtones. If you play guitar or violin or something like that, you also understand about overtones, harmonics. That's what those literally are. And they seem to show up. There may not be exactly 4 of them, and they may not be in exactly that place. But I usually see them round and about 1,700 to 2,000 wave numbers, give or take, somewhere in there. And if you see a few nice little peaks like that, typically that's a sign that you've got an aromatic compound. And again, don't take my word for it. Look up a bunch of aromatic compounds. That will show you what the kind of variations are in that pattern that you can expect. But we talked about patterns the first day of class. So that there is, I believe, a pattern you can trust. If you have an aromatic compound, you will see a few of these overtone bands. If you want to get an idea of possible variations within that pattern, like I said, the very best thing you can do is to look up spectra yourself. There's no list of rules that I can give you that will do, even if I could come up with it, which I doubt. There's no list of rules I could give you that would do you 1% as much good as just going and looking up spectra. I'll be saying the same thing when we get to mass spectrometry, which I believe will be Monday. Same thing when we get to carbon NMR, and same thing finally when we get to proton NMR. The best way to get experience, well, is by getting experience, by going and looking at actual spectra. So from this, I think you can see there are, again, some subtle differences. And as for some of these peaks here, we probably could identify some of these. Generally, round and about 1500 wave numbers, I usually think those are probably carbon-carbon bond stretches within the aromatic ring. Some of these lower frequency ones might be CH bending vibrations. I certainly am not concerned to identify every last one of those peaks. From this, I would know that I'm looking at an aromatic compound with at least one sp3 hybridized carbon, so some kind of alkyl benzene. But again, I don't see any carbonyl, I don't see an alcohol or a phenol, I don't see the carboxylic acid, certainly. And that's basically what I would derive from this. Can't think of anything else to say. Questions on toluene? Don't see Bella, and I'm a little bit worried. And as you can see, I've put basically what I'm saying in terms of the description. That's also in your class notes. Good. So what about carbonyl compounds? Cyclohexanone, well, I think we can do that. I can maybe make cyclohexanone from my benzene. Actually, I should have left that one bond in. There's your cyclohexanone. We haven't officially learned how to name ketones yet, but I think that name will shock no one. Cyclohexane, cyclohexanone. So that's the structure of cyclohexanone. So what have we got here? Well, we've still got CH stretches below 3000 wave numbers. As we would expect, we've still got these 5 CH2s over here. And we would expect those CH stretches to be below 3000 wave numbers. I see nothing above 3000 wave numbers, nothing worth mentioning. So that makes me think there's no sp2 hybridized carbons apart from, of course, the carbonyl carbon. That's obviously sp2 hybridized, but no sp2 CH stretches. No alkene or vinylic type CH bonds here. The main feature of this spectrum is this extremely strong and broad peak. Oh, what do you want to call that? Shall we say that's 1720 or 1715 wave numbers, somewhere around in there. Very typical for ketones, for aldehydes, things like that. You could distinguish ketones from aldehydes from the aldehyde CH stretch, which I don't see here. I believe those are pretty strong and show up roundabout here somewhere. So I would, as usual, I would not know looking at this spectrum that it's cyclohexanone, but I would know that I'm looking at a carbonyl containing compound that is otherwise saturated, probably an aliphatic ketone or something like that. So I don't really see too much of anything else. And again, some of these weaker peaks might be CH bending or something like that. But certainly, if this were, let's say, a matching question, I would look for a ketone that's otherwise saturated and would expect to find one. So, but carbonyl peaks are very easy to pick out. And regardless of the type of carbonyl compound, whether it's a ketone, an aldehyde, a carboxylic acid, an ester, whatever it may be, they're all round and about 1700 wave numbers for the CO stretch. Some of them might go as high as 1800. How can you tell ketone versus aldehyde? Well, the aldehyde will have the aldehyde CH stretch. and the ketone will not. Again, the best thing you can do in order to figure out what you'll need to know is look up some aldehydes and compare them to similar spectra of ketones. So look up the spectrum of hexanal. You know, I don't think I have an aldehyde here, but that will do you far more good than anything I can tell you, than any lists of facts that I can give you. But I'm sure you'll be able to see the difference. The CH stretch on the aldehyde should be very prominent, and I think you'll find it's very easy to tell a ketone from an aldehyde. Less easy is telling an ester from a ketone, though I think we have an ester next. Again, I've described all that, but this is the spectrum of ethyl acetate, and those are a little bit difficult to tell from each other. I don't know that I would be able to, well, again, 1740 instead of 1710, it's a little higher than the ketone carbonyl stretch, still very prominent, I think you'll agree. Let me draw the spectrum of ethyl acetate for you. I'm sorry, the structure of ethyl acetate. There you go. It's the ethyl ester of acetic acid. So that's the structure of ethyl acetate. And again, I might be able to tell the difference between the two because they're otherwise rather similar. You've got your CH stretches again below 3000 wave numbers, just like we did before. This is at something like 1720. This is a teeny bit higher frequency, more like 1740 wave numbers. This is sort of on the edge of what we might be able to tell the difference from. But I'll tell you, and again, I've put an old exam on eCampus. You can get an idea from that. But I would not be shocked if you found on that old exam the spectrum of, say, an aromatic ketone and an aliphatic ester, or the opposite, an aromatic ester and an aliphatic ketone. That would be very easy to tell apart because you'd be able to see the sp2 hybridized CH stretches. So that would be, this is sort of just over the line, just barely fair. But something like that, one's aromatic and one's not. That's absolutely fair game. And again, remember, you've had a semester of organic chemistry already. You know how this works. If you feel like you leave class not knowing exactly what you look to know, that's typical. You have to practice. And the OWL assignments play a role in that. But I think really chief in terms of the practice that you guys will do on spectroscopy is looking up spectra on your own. It's the best way to learn. That's basically how I've learned it. I've taken a bunch of spectra over my life. I've taken IR spectra. I've taken proton NMR spectra. I've seen a bunch of them. So I don't have how to put it, I don't have a correlation table memorized. But from having seen hundreds or thousands of spectra, I've gotten the patterns down. And that's what I think you will do too as you look at more spectra. So, let's see, ethyl acetate, there you go. So similar to the ketone, maybe just barely distinguishable, but certainly we can pick out the carbonyl stretch, and we can tell again, there's certainly no sp2 hybridized carbons bearing hydrogens. I don't see an aromatic ring, I don't see an alcohol, I don't see a carboxylic acid. Those are the first things that really jump out. I want to make sure I leave some time for our reef session, since we're just going to have a practice reef session today. It will not count towards your grade. Those of you who have already added into the class and have your reef app up and running, you can register your attendance. Sometimes in class that will be all we'll do is we'll register attendance, and you'll just get 100 out of 100 for attendance for the day. Other times we'll do reef polling, and we'll practice that today also, so you can see sort of how that will go. Good, everyone comfortable with the ester then? Oh, I need to change that. OTBE, I like to use that sometimes. I thought I changed all of them. But if you ever see OTBE in my class notes, it stands for other things being equal. You can do read through computer as well. That's good. I was wondering about that. Good. So basically, I've already summarized everything here. So the two more that I want to be sure that I show you, and I mean, we could go on forever with alkynes, terminal alkynes, we could do nitriles, we could go on forever. But the two that are the most important that I want to be sure that I show you are alcohols and carboxylic acids. And they stick out like anything. They jump right out at you. So here is a typical alcohol. This one is 3-pentanol. And again, we haven't officially learned how to, well, I guess we did learn how to name alcohols. We did chapter 17. But I think that's something that you could probably come up with the structure given the name, 3-pentanol, so 5-carbon chain, and the OH group is in carbon 3, 3-pentanol. And I think everyone can see this nice, broad, very beautiful, very symmetrical, very smooth peak over here. And that is your OH stretching frequency. And where are we going to put that? What do you want to call that? 3350, maybe 3400, very typical place for those to show up. And that's the first one we've seen of this type. And boy, it just jumps right out at you, doesn't it? So nothing else looks like that. Nearly all alcohols will have that type of smooth, symmetrical, pretty, and broad peak like that. The only time you don't see it is if basically the reason the peak has that shape, and again, to go to first principles on this would be beyond the scope of this course, but I can tell you that the direct cause of that particular shape is the hydrogen bonding that alcohols undergo. And so the only time you won't see that type of broad, pretty peak in an IR spectrum of an alcohol is if there's no hydrogen bonding, or in other words, if you've got a really, really, really huge alcohol, 15, 20, 30 carbons, then it might not look like that. And if you want to know what that might look like, again, best thing you can do is try to find a spectrum of an alcohol like that. Look up, pentadecanol, or forget what the 20-carbon compound is called. Icosanol or something like that, maybe. Good, but from this we can also tell, again, there's certainly no carbonyl. I don't see any of those strong peaks at or around 1700 wave numbers. All of my CH stretches, meanwhile, are below 3000 wave numbers, so I do not expect that there's an aromatic ring or carbon-carbon double bonds. As usual, I could no more tell this is 3-pentanol than 2-pentanol. Though you could probably look up both of them and see how they differ. They're probably almost identical with only very subtle differences. But certainly I would know by looking at this that I've got myself an aliphatic alcohol. There's no carbonyl or any other type of functional group besides. But alcohol functional groups jump right out at you. They always tend to look like that. Oh, and here you go. The IR spectrum of 3-pentanol shows a broad, smooth, strong resonance at around blah. This is the OH stretching frequency, blah, blah, blah. Again, note the saturated, otherwise there's little to interpret. Good. So look up other spectra of alcohols, and I think you'll be able to convince yourself that they will all have this in common, at least if they're small or medium-sized alcohols. Can't think of anything else. Make sense? Actually, I got an idea. Let's do our carboxylic acid. This is a very typical carboxylic acid spectrum. And in a pentanoic acid, so CO2H, carboxylic acid group. So there is also an OH in carboxylic acids, as you know, and also we of course have the carbonyl, and we can see the carbonyl stretch very strong here at about, again, shall we call that 1710 maybe, something like that? It's very typical for a carboxylic acid. Beyond that, we also have our OH stretch, and as beautiful and smooth and pretty as the alcohol OH stretches, it is exactly that ugly for a carboxylic acid. Exceedingly broad, very unsymmetrical, and probably obliterating or almost obliterating any of the CH stretches. And we can kind of see them peeking out here, no pun intended. Looks like they're all still below 3,000 wave numbers. So we would expect a saturated compound other than the carboxylic acid, but very ugly and pretty much obliterating most of the high frequency end of the spectrum. And again, if you compare, it's also called valeric acid, by the way. That's the common name of pentanoic acid. You can use either name. But as pretty as the alcohol OH stretch looks, the OH stretch of a carboxylic acid is ugly. And like I said, pretty much covers up a goodly chunk of the upper frequency end of the spectrum. So again, something that also will really jump out at you. Don't forget also a carboxylic acid will have a carbonyl, whereas an alcohol, short of having other functional groups present, will not. So that's an easy way of telling the two apart. So that's pretty much, I already told you about that website. I've given you a step-by-step method to use in order to learn this material. And since we still have a couple minutes besides what we need to do our practice repulling session, heck, why don't I look something up? I think that would make a lot of sense. We had a question about how can you tell an aldehyde from a ketone? Let's find one. I think that makes some sense. I think I even have this bookmarked. Unless, of course, I don't. Okay. This also gives me the chance to show you how to use this website. So first thing you do, you're going to need to accept the disclaimer, which I will not hold them responsible if I am harmed from using their website. All right, let's look up an aldehyde. How about hexanal? 6-carbon aldehyde. Do they have the IR spectrum? Yes. And they also, we're not even going to talk about Raman. And they also have the mass spectrum, interestingly, the carbon NMR, but not the proton NMR. So they won't necessarily have all of them. I assume all of you can see this, right? I believe I'm sharing my whole screen. Yes, we should be good to go. So let's look at the IR spectrum. And there we go. And lo and behold, this peak down here, it's usually significantly below 3,000. That one there, I believe, will be the CH stretch. And you can, actually, it might even tell us, does it? No, it seems that it doesn't. Well, that's lazy of them. So you'll notice that's significantly separated from the CH stretches here just below 3,000. So that's what I look for in terms of telling an aldehyde apart from a ketone. It's interesting that the carbonyl stretch is so much broader. I don't know that that will always be the case, but certainly the aldehyde CH stretch stands apart from the regular sp3 hybridized CH stretches. Other than that, I would get from this that I don't have an alcohol, I don't have any aromatic rings or alkenes. I certainly would not know that this is hexanal as opposed to pentanal, but I certainly can tell that I'm looking at a saturated aldehyde, that the only unsaturation is in the carbonyl group. So that answers that question and shows you how to use this website all in one fell swoop. Make sense? Everyone reasonably happy with that? Let me then. So that's how you use that website. I really can't recommend that enough. Actually, let me do this. Good, I just want to get that ready for the next section. Okay, so let's do our practice clicker set, or practice reef pulling session. Let me, this is reef pulling, it's partly for me, by the way, because it's been a while. So what I'll do is, I'm hoping, slideshow, from beginning. Good, and lucky us, everything that we need stays on screen. Good, so first question. Again, this doesn't count towards your grade anyway, but what I'll do is I click on this green arrow, and then you should be able to register your responses. So this is not the same as taking attendance. You should get brief questions on your screen there. If it's not working, what I've heard is that you can still select A, B, C, D, E, but this is what a typical brief polling session would look like. And generally, I would let it go about 2 minutes. No, I will not always give the answer away like I did this time. This is just practice here today. But the other thing I should say while we're waiting for this is that good news and bad news about the Reef app that you can look up. I think you can look it up in your cell phone. I know you can look it up on the computer too. So you should be able to check if your setup is working. Even in yeah, you do need the subscription to do Reef polling. So that's why I didn't make it count today, because I figured there's some people who, I feel bad. I mean, I want you guys to spend not one dime more than you have to. But like I said, I'll try to make it worth your while by doing a Reef polling at least once a week, maybe not every single day, sometimes twice a week, maybe. But what else is it going to say? So you can look it up on the Reef app, and you can confirm that it's working. And you can confirm that it both registered your attendance and registered your responses. Like I said, it doesn't count today. This does not count towards your grade. Maybe we'll start on Monday. And I don't know if I'll do a polling session or just attendance, but we'll do one of those two on Monday. The other thing, if you sign into Reef every day for attendance, probably, yeah, we will at least take attendance. And I believe you're able to do that just on the free side of the app. So you'll only need to use the polling one when we're actually doing polling like this. I do want to warn you all, though. The Reef app is very bad at getting your exact Reef grades right. Take those with several teaspoons, maybe even an entire cup of salt. I will eventually put up your Reef grades little by little on eCampus as we get them. And so anything you see on eCampus in terms of Reef grades will supersede what you see on the app, because it's probably wrong. For example, I would not be surprised if you see classes you have zeros in for attendance that day. Well, those are probably my other 228 section and my 227 class. Of course you have zeros in those, you're not in those classes. So you see what I mean? It doesn't tend to get it right. All right, so what I would then do at this point is I will check your answers, and I will mark which one is correct. And even if I forget to do that, by the way, it will still, I can always do that later. So the next question is, in organic molecules, what type of transition do infrared photons cause? And again, I may or may not be giving it away, at least if you look real closely. I will not typically do that, but since it doesn't count anyway, hopefully that's the answer you would have picked. Yeah, I know. I've learned that even if you're not colorblind, it's a little hard to see. But I will be able to go back after class. I will always post these on eCampus. So yeah, I meant to do that. Maybe I'll do that in between the two classes since I have half an hour. So yes, you'll always be able to see these for studying, and I'll always put the answers. So I think that's just about everybody. Good. So it actually is hard to see. But this is slightly bluish to my eye. So and I'll give the answers like that. Let me mark this one that way, and that should do it. So actually, we're pretty much out of time on. On Monday, I'm thinking we're probably doing mass spectrometry, which technically is not spectroscopy. It's not quite the same type of critter. You'll hear people sometimes calling it mass spectroscopy, but really that's incorrect. It should be called mass spectrometry. So that will be Monday. I'm going to get this uploaded to eCampus, this Flickr session, or Reef session, and I'm planning on getting your OWL assignments up, let's say today or tomorrow, your first OWL assignments. Of course, nothing's due today. Anything graded will be due at earliest next Friday. So other than that, we're out of time. So have a great weekend.